Hello students, today we'll start a new topic on optics or wave optics, that is diffraction of light. The diffraction of light, we'll try to first understand that what is diffraction of light, what is the main mechanism behind the diffraction of light. Then we will slowly go towards the classifications of diffraction. We'll try to understand the diffraction fringe pattern. Then we will see what are the basic differences between diffraction and interference. Then we will see some applications of diffraction. So let me start with a very simple thing. If you have ever gone through the Feynman lecture series, Feynman lecture series 2, volume 2, this starts with one basic problem of diffraction. The problem was like that: suppose I am having a narrow slit here and there is a screen, and through that narrow slit, the slit is that narrow that through which if I send any electromagnetic radiation, or say for simplicity of understanding electron beam, only one single electron can pass through the narrow hole. Then it is guaranteed that because of the rectilinear propagation of light, at that particular point I should expect the electron to fall on the screen. But according to quantum mechanics, what you can see, because of uncertainty principle or Heisenberg's uncertainty principle, that the position of electron on the screen will be uncertain. That can fall anywhere on the screen. If one single electron is traveling through that, then also one single electron, it is traveling through the slit, it should flow in a straight line. But according to this Heisenberg's uncertainty principle, we have seen in quantum mechanics, there will be some uncertainty in the position of the electron on the screen. So this is because of the diffraction mechanism. So we'll see diffraction mechanism from two different perspectives. One is the wave optics, that through the wave optics we will consider the light is flowing in form of the wave and it follows rectilinear propagation. Also we'll see diffraction from the point of view of corpusculous nature of radiation, that is light. It consists of several photons. These are the smallest ever energy consideration in the universe. The energy of each photon is equals to h nu. Photons are traveling in a particular direction, that is why you are getting light. So let us start with some very basic thing, that what is the definition of diffraction and how we are getting diffraction. Suppose I am considering a sharp edge of the obstacle, that may be any sharp edge of the obstacle, that may be a knife edge, that may be the edge of the shaving blade, anything. And I am having some light source here, this is the source of light. I am having a screen here, this is the screen. So from the light source, light can go in any direction in a straight line like that. So it will also collide on the sharp edge of the obstacle, and just touching it, it will fall on the screen here. So on the screen I cannot get any light in this region because there is one obstacle. Light flows in a straight line, so in this region I am not getting any light. This region will be called geometrically shaded region. This is a region which is called geometrically shaded region. Always I am expecting darkness here. But according to diffraction, or according to the definition of diffraction, or if you see it empirically, if you are having a source of light here, you are having a sharp edge of an obstacle. I am repeating it, sharp edge, not any type of edge, sharp edge of any obstacle, then it is possible to get some light in the geometrical shaded region. Get some light in the geometrical shaded region like that. So is it like that, the light is bending from the sharp edge? But we have understood the light flows from the straight line. So how can I expect some light in the geometrical shaded region? Then came the Huygens principle to explain it. Huygens principle tells that diffraction is nothing but interference between the secondary wavelets or secondary wavefronts. Then automatically the question will arise, then what is Huygens principle and what is the secondary wavefront, and if this is the secondary wavefront, then which one is the primary? Huygens principle, it tells that if you are having a source of light, suppose I am having a source of light and it is sending light in all possible direction in the form of sphere. Suppose you are considering a point here and it is blinking like that, and it is sending some light in the spherical wavefront. The spheres, these are going big, 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 and they are vanishing. This is the spheres, and this is another sphere. This is another sphere. This is another sphere in 3D. So these particular spheres or perimeter of the spheres, or if you consider in 2 dimension the perimeter of the circles, this will be called the wavefront. What is the definition of wavefront? The definition of wavefront is that all the photons on that particular wavefront are vibrating in the same phase of vibration, or in contrary you can say the locus of all the photons which are vibrating at the same phase of vibration is called the wavefront. So consider this to be one wavefront. Now this is the source of light. So from the source of light I am getting the wavefronts, and this will be called the primary wavefronts. Once the primary wavefront is colliding with any sharp edge of the obstacle, then the particular photons which are colliding on the surface, they will behave as the secondary source of light. Secondary source of light, as if they will be sending now their own wavefronts like this. So this is not that one single electron is colliding or one single photon is colliding on the surface. There will be several photons which are colliding on the surface. So all will be sending their individual wavefronts like that. So these are now behaving as the secondary source of light. So this is now being converted into primary source of light, and these are the secondary source of light which are colliding on the surface of the obstacle. Now see, the secondary wavefronts generated from the secondary wave source of light, they are colliding in their path and they are colliding on the screen. So you have already seen that two lights or two light waves coming from space or coming from two different sources, S1 and S2, colliding at a point in the space or in the screen may generate the interference fringe pattern. And what is interference? Consecutive darkness and brightness. So remember, I was getting the geometrical shaded region, I used to get, and I was getting total darkness, but now I am getting consecutive darkness and brightness here, and these fringes are overlapping with each other. Several fringes are there because of secondary, because there are large number of secondary sources and there are large number of secondary wavefronts which are colliding on the screen. So I am getting consecutive darkness which are overlapping with each other. So there is highly possible that in that region I am getting light to some extent, not fully illuminated. This region will not be fully illuminated, this region will be fully illuminated, but this region, geometrical shaded region, because of diffraction I may get light to some extent. And why I am getting this light? I am getting this light because of the interference between the secondary wavefronts, and the whole phenomena will be named as diffraction. So as you can see, the diffraction will always be associated with interference, and diffraction is nothing but you can call it is nothing that interference between the secondary wavefronts. So now if you start classification between interference and diffraction, so you make a table like that. In this region you write this region I am writing interference in the left hand side, in the right hand side I am writing diffraction. So I am trying to understand the classification between interference and diffraction, or the difference between them. The first difference I already got, that interference is nothing but the superposition between the primary wavefronts or primary sources of light. It can create interference, or you can call it primary wavefronts. And in the diffraction it will be caused because of secondary source of light and because of superposition of secondary wavefronts. So this is one difference, and this is very vital difference. Second one, In case of interference, you have seen in the interference fringe pattern, suppose this is the interference fringe pattern, you have seen that fringe width of all fringes are same. So if this is bright fringe and this is dark fringe, one bright fringe, another dark fringe, consecutive bright fringe and dark fringe, like that, the fringe width of the bright fringe as well as the fringe width of the dark fringe all are same. But in case of this diffraction, in case of diffraction, the fringe width may differ. The fringe width that may differ, that is the fringe width of all the bright fringes and fringe width of all the dark fringes are not same. If you see one diffraction fringe pattern, the fringe pattern looks like this one. You can see this is the fringe width of the principal maxima, this one, and these are the secondary maxima. So fringe width of all the maxima are not same, as well as all the minima are also not same. Third vital difference is intensity. Intensity of all maxima same, but here intensity of all maxima are not same, that may differ. Then you can see from this spectrum, and I will come to that point, I will come to the spectrum later, I will elaborate this one. Fourth difference, that minima is not always darkness. Minima is not always darkness, because you have seen the condition for minima to be dark, you have seen that the two sources should send wavelength of exactly same amplitude, that is A equals to B. If only A equals to B, then only you are expecting the minima to be a darkness, intensity equals to 0. But I mean equals to 0 in case of interference, you have seen that. But in case of diffraction, minima equals to darkness always. This is guaranteed. This is the feature of diffraction. Now we will look at a particular problem of diffraction with single slit. This is a very basic problem and fundamental problem of diffraction. Diffraction with single slit, or you can call it Fraunhofer diffraction with single slit. Diffraction may be classified into two groups: Fraunhofer diffraction and Fresnel diffraction. Diffraction with single slit. And this is the class of Fraunhofer diffraction. What is the difference between Fraunhofer diffraction and Fresnel diffraction? In case of Fraunhofer diffraction, the source and the screen should be separated infinite apart. The source and the screen, suppose this is the source and this is the screen, they should be situated at an infinite distance, that is Fraunhofer diffraction. But in case of Fresnel diffraction, they should be at infinite distance. I am trying to sketch the Fraunhofer diffraction with a single slit first. Let us see, suppose this is the source of light and there is one lens. From the source of light, light will be emitted in all possible directions, and this lens will converge the light and make it parallel beam. Now at that point I am positioning a single slit, a very narrow slit. How narrow? Narrow to what extent? There is also limit of diffraction. What will be the limit of diffraction? Always light entering through a narrow hole will not give you diffraction. You can see, as for example, suppose you are having one window in your room and sunlight is coming through the window, your room is being illuminated, but you are not getting diffraction, that is consecutive darkness and brightness. Why? Because it is not satisfying the principle. Always the slit width, this is the slit width, suppose it is A, slit width should be of the order number of the wavelength of light used. This is the main fundamental prerequisite for diffraction. That is, the slit width should be always of the order of the wavelength of the light. Otherwise, you are not getting diffraction. Otherwise, if it is lower, if the value of this slit is lower than lambda, you are not getting any light. If it is much more higher than lambda, then you are getting general illumination, as we are getting through the window. So this slit, suppose you are using sodium light here. For sodium light, what is the value of lambda? 6328 angstrom, sodium yellow light, and that slit width should be that narrow. So passing through the slit, based on the Huygens principle, the light will bend, it will change its path, it will bend in this direction, or it can go upwards also. I am sketching for a particular direction only. Then you are positioning here another converging lens. It is converging the light on a particular point, and position a screen here. On that screen, you will be getting the diffraction fringe pattern. And how the fringe pattern will look like? At that point, at that particular point, you will be getting the principal maxima here. Then consecutive minima and maxima both the sides. And the intensity of the maxima will go on decreasing as the order number is increasing. It is maximum for the central spot, then it is going on decreasing slowly, gradually it is going on decreasing as the order number of the fringe is increasing. This should be the intensity distribution pattern for the single slit diffraction. Now we'll see why we are getting such pattern. Let us consider a particular problem and try to solve it mathematically, that in case of diffraction what really we are getting. So let me consider that this slit width, equals to A, and I am trying to magnify this region, because as I understand from this figure till now, everything is happening in this region where from the light is bending. Otherwise the principle is very basic. Light coming from a source, it is bending from the slit, then it is again there is first lens is L1, second lens is L2. With that lens it is converging at a particular point. On that point we are getting diffraction fringe pattern, and on the screen I will be getting consecutive darkness and brightness. If I plot the intensity distribution pattern, that in this direction I am plotting intensity, in this direction I am plotting the distance from the central spot, then I should get the distribution pattern or intensity distribution pattern like that. Why I am expecting this one? This is the main question now. I am considering the slit width to be A. I am trying to magnify this region. Then what is happening here in this particular region? So let me consider this is a slit. Width of the slit is A. This is a slit, and I am concentrating on the midpoint. Suppose the midpoint, this is the midpoint. Light is coming from this direction. This is the light coming from a particular direction, parallel ray of light, and from the slit, suppose it is bending in this direction. Because of Huygens principle, I have already elaborated the Huygens principle. This is not guaranteed it will deviate in this direction. Also it may happen it is going in this direction. This may also happen. For simplicity of calculation, I am considering only one direction. It may bend in any direction. Suppose it is coming from this direction, then bending in this direction. Also it can bend in this direction. Any direction it can bend. It depends. So what I am considering the midpoint. Suppose this midpoint, and I am considering another ray, this ray. Suppose I am considering the ray A and ray B. A is coming through the midpoint, and let the midpoint be any point O. And I am considering another ray or the consecutive ray which is passing through a distance x from the midpoint. This distance is x, from a distance x from the midpoint. That is I am considering this point to be P. Suppose OP equals to x. Now let me consider the angle of diffraction. Angle of diffraction is what? The angle by which the ray has been bent. That is the angle of diffraction. The angle of diffraction let this angle of diffraction be alpha, and okay, I'm considering angle of diffraction to be theta, and angle of incidence to be I. So in this particular figure, what will be theta and what will be I? You can see anywhere. Suppose I am drawing a perpendicular line here on that point. So angle of incidence, this is the angle of incidence, and this is the angle of bent or angle of diffraction. You concentrate on the figure, this is I and this is theta. So similarly, if I calculate here, it will be I and this will be theta. Here also this will be I, this will be theta. So I am trying to calculate the path difference between the rays from A and B. That is, I am trying to calculate the path difference between these two rays which are traveling through the midpoint and from a distance x from the midpoint. Okay, I am trying to calculate the path difference between these two rays, this ray and that ray. So how to calculate the path difference? We have already seen, to calculate the path difference, the simplest way that you draw two perpendicular lines here from O on B and from O on this line. Let this be OM and this be ON. I hope you can see this OM and ON. Two perpendicular lines I have drawn. So path difference will be actually equals to PM plus minus Pn. Why I have used this plus minus sign? Because I have already considered that light is bending in this direction. If not, light is bending in that direction, then it will be subtracted. Otherwise, it will be added. That's why I am using this plus minus sign. Otherwise, both the rays are traveling equal path. From this point to that point, path is same. From this point to that point, the path is same. Only the difference lies from this region and that region. Otherwise, the path is same. So path difference equals to PM plus Pn. Now you consider these two triangles, this triangle OPM and triangle OPN, these two triangles. So from this triangle OPM, you can write the value of PM, you can write the value of Pn as x sin I. You can check it out. This is I and this is theta. So by geometry, this is 90 degree, this is 90 degree minus I, so this will be I. This angle will be I and this angle will be theta. This will be theta and this angle will be I. So this will be x sin I and this will be plus minus x sin theta. So you can write it as x sin I plus minus sin theta. Simple. I am writing it as x phi, this path difference. So what is phi? Sin I plus minus sin theta is phi. I am considering this for simplicity of calculation. Now I am trying to calculate the phase difference. Phase difference, what is the formula? Phase difference equals to 2 pi by lambda into path difference. Okay, so the actual value is 2 pi by lambda into x phi. This is the phase difference. Phase difference is been calculated out. If I calculate the phase difference, then I can easily calculate the conditions for maxima and minima. I am going towards that side. Now let me consider that the displacement of the ray coming through O, displacement of the ray coming through the point O, it is equals to, it is r e to the power I omega t plus delta, where delta is the phase part. I am considering one single ray. But in case of diffraction, I have to consider all the rays which are passing through the slit. Then let us consider that k is a function, k be the number of rays through unit clear space, through unit space. Now what will be the number of rays which are passing through dx, any region dx? The number of rays passing through any region dx will be equals to k dx. So the displacement of all the rays passing through any region dx, suppose this region is dx, any region dx, that will be equals to dy will be equals to k dx r, this one r e to the power I omega t plus delta. So for the whole slit, this equation will be integrated. Y will be equals to integration of dy will be equals to integration k dx r e to the power I omega t plus delta. Then important part is what will be the limit of the integration. See, I have started from the displacement of the ray coming through O. O is the midpoint. Then I considered any space dx. So if I consider this is the total slit width, and I am concentrating on the midpoint, and slit width I know it is A, slit width is A, that I know. I am concentrating on the midpoint, so I have to go from the left end and to the right end, furthest point and this furthest point. So what will be the limit? The limit will be minus A by 2 to plus A by 2 to make the whole aperture to be A. So limit of the integration will be minus A by 2 to plus A by 2. Now you integrate. This is the simple integration. You have to just integrate now to understand the else. Integration, some terms will come out of the integration which are not dependent on that function. So this will come out of the integration, kr e to the power I omega t, this will come out of the integration, and within the integration you are getting only minus A by 2 to plus A by 2. Then e to the power I delta. Then what is delta? Delta, we have seen that delta equals to nothing but x phi. Delta equals to the phase part, and phase we have calculated. Phase just now we have calculated. What was the value of the phase? Phase was 2 pi by lambda into x phi. So phase part delta, that is equals to twice pi by lambda into x phi. Put the value here, I e to the power I 2 pi x phi by lambda dx. Just you have to integrate this one. How to integrate this one? Integration is very simple, kr e to the power I omega t. Then integration will be e to the power mx, that is e to the power mx. What will be the integration of e to the power mx? E to the power mx by m. So it will be e to the power I, then 2 pi x phi by lambda divided by I 2 pi phi by lambda. Limit of the integration is minus A by 2 to plus A by 2. Put the values now. This will be kr e to the power I omega t. Then first put plus A by 2 instead of x. Then 2 cancels out. You are getting e to the power I pi A phi by lambda minus e to the power minus I pi A phi by lambda divided by I 2 pi phi by lambda. Simple. Proceed further. We are calculating y to be this function. So do you know the simplest form of this one? That is, if I am getting a term, suppose e to the power x, what is the expansion of e to the power x? The expansion of e to the power x is, or consider a function e to the power ix. So this will be cos x plus I sin x. So what will be the form of e to the power minus ix? This will be cos x minus I sin x. So if you add this one, e to the power ix plus e to the power minus ix, you will be getting this function plus that function. That is, this imaginary part will cancel out. No, this plus this will cancel out. Only the real part will remain in the plus function. If you get a minus function, this minus this one, then the real part will cancel out, only the imaginary part will exist. So look at this function. You consider that e to the power ix, this function to be x, and this is e to the power minus ix, minus function, so only the imaginary part will exist, the real part will vanish. You can try this calculation at home. This is simple calculation. So this will be kr e to the power I omega t, then twice I sin pi a phi by lambda divided by twice I pi phi by lambda. I am rewriting this one as KAR. I am intentionally adding this a here. KAR e to the power I omega t into twice I sin pi a phi by lambda divided by a is being added here. So here a will be added again, twice I pi a phi by lambda. Now I am considering this 2i will cancel out. I am considering a function that pi a phi by lambda, this function is alpha. So I am writing y equals to KAR e to the power I omega t, then sin alpha by alpha. So this is nothing but the displacement of the wave, or all the waves passing through the slit. This is the slit passing through the slit. This is the displacement of all the waves. So if we know the displacement, or if you know the nature of the wave, how can we get the intensity distribution pattern? That is very easy. From the wave part, you have to understand which one is the amplitude part and which one is the phase part. Square of the amplitude will give you the intensity. So in this equation, which one is the phase part and which one is the amplitude part? This part is the phase part. Rest of the part is the amplitude part. So how can I express this one? I can express this one as the amplitude part, A will be equals to KAR, then sin alpha by alpha. I can write it as A equals to A0, a constant part. This part is constant, A0, then sin alpha by alpha. This is the amplitude. So what will be the intensity? Intensity will be equals to A square. That will be equals to A0 square sin square alpha by alpha square. A0 square, this is also constant. I can write it as I0 sin square alpha by alpha square. This is I. This intensity expression for the single slit. I equals to I0 sin square alpha by alpha square. The end result is very small and beautiful, as is expected in case of physics. So from the intensity distribution pattern, now I can draw the from the intensity expression, I can draw the intensity distribution pattern, and I can easily calculate now the conditions for maxima and minima, and that will be followed in the upcoming next video.